And some springs can do both. They're in a state where they can stretch and compress. So it might be in a state like this. This is its normal state, and we might be able to put a force on each end. And cause it to compress. Or we can take that same spring and pull on the ends and cause it to stretch. Okay, some springs can do both. Some springs are only designed to be stretched. Some are only designed to be compressed. But for most of our cases, we'll assume the spring can go in both directions. All right, so I've been ignoring the fact that force is a vector quantity. And all we've been looking at are magnitudes. If you really want to be correct and write a vector equation, force is always opposite the direction of the displacement. If we stretch the spring by pulling it down, the spring pulls back up. If we compress the spring by pushing it up, the spring pushes back down on us. The spring always pushes opposite the way it's displaced. If it's compressed, it pushes out. If it's stretched, it pulls back in. So the spring force is always opposite the direction of the displacement. So if you write it in vector form, you need that minus sign. F equals minus kx. So a lot of times you'll see that, but usually the way you use this equation is you just use it to find you ignore the minus sign, you find the magnitude of the force using this equation, and then you look at the situation and figure out what direction the force is. Okay, there's our, this, I guess I should put a spring, indicate this is from a spring. And that's the spring constant. And that just depends on the spring, right? The material it's made out of, how it's wound, how thick the wire is. If the spring is soft, that's a small number. If it's very stiff and hard to stretch, that's a big number. Okay, so those are springs. We good with spring forces? The next thing we want to do is talk a little bit about work. And then we'll figure out what the work is from the spring. So we've already talked about work. Force times distance, right? If the force is constant, the work, that's work, is force, and it's a dot product with the displacement. It's the force times the distance times the cosine of the angle between them. So if F is constant and in the direction of the displacement, then we get something like this. The force is constant over the displacement. Then the area under that curve, what's the area under that curve? It's the force multiplied by the displacement. You see that? which is the work done. The work done on our object by F. So this is not a lucky case where when the force is constant, we get this work, the area under that curve is the work done. The work done is always the area under the curve. So even if our force changes, and we want to know the work done on our object as it moves from, doesn't matter, from x equals x1 to x equals x2. And the force does something like this. We can find the area under that curve, and it equals the work done. Work done on our object by F as it moves from x1 to x2. Okay? So our box might be sliding this way, right? But our force is in the other direction. Then what do we get? We call to the right positive. So delta x is increasing in the positive direction. That means that F has to be negative. Let's call this, what should we call it? F sub x. So the area under our curve is this thing. And what is that? It's going to be negative. Right? When the area is underneath the x-axis, it's negative area. When it's above the x-axis, it's positive. We get a negative number now when we calculate this area. And the work done is negative, right? Because the force is going opposite the displacement. It's slowing the object down. So it's the component of the force in the x direction.